Hi, I'm Owen Calder, and this is Lab 6. In this lab, we drop a bar magnet through a tube of aluminum foil and measure how long it takes for the magnet to come out again. We use a magnet with a dipole of 7 amp meters squared, and it takes an average of 0.26 seconds to fall through the 0.5 meter rod. Some important equations are the equations for force on a wire due to a magnetic field, the B field due to a magnetic dipole, and the resistance of a substance, and then the rate change of flux. In the experiment, we take a rod wrapped in aluminum foil. It's surrounded by the lab, any nearby electronics, and Earth's magnetic field, but those shouldn't affect the experiment. We measure the rod's properties. It's 0.45 meters long. The aluminum is 1 centimeter thick. We then drop the bar magnet into the tube and measure how long it takes to come out. We measured it 5 times, and the average was 0.26 seconds. We then simulated this in a computational model. Magnets here, it goes through a thing, and its velocity is graphed as a function of time. It starts quite slow, and then suddenly, and then increases, or speed increases linearly, and then drops, or then increases very suddenly. We simulate this by breaking the rod into a bunch of current-carrying rings. The model calculated that the magnet should stay in the tube for 0.65 seconds, which is much greater than our observed time. For coding, I made some functions to calculate the rate change of flux with respect to time using that equation from before. I just implemented it with Python. Here's the function for the dipole, or the B field due to dipole. It's just using the same equation from before. And here, calculating the force on the magnet. Some possible sources of error include measuring. There may have been some inaccuracy measuring when the bar magnet came out of the tube. The model also assumes that the rod is solid aluminum, but it's actually loosely packed foil, which could inhibit the current. If the resistivity of the foil was 0, no current would be dissipated by heat, and the magnet should levitate infinitely. If there were holes in the rod, less current would flow, and the forces acting on the magnet would be less continuous. It would kind of oscillate a bit. In conclusion, the magnet falls through the pipe and is slowed down by the current it induces, which was demonstrated in our computational model. We used Newton's third law, Faraday's law, and the law of Biot-Savart to calculate the forces and simulate the falling magnet. The experiment was not as inclusive, falling through in 0.26 seconds, which is similar to what it would have been if it were a regular non-magnetic object. Thank you. you.